Hello, everyone.
Today's topic is expressions using letter numbers.
Algebra begins when mathematics stops depending on exact numbers and starts describing relationships. Suppose a school charges 18 rupees per notebook. Instead of calculating separately for 5 notebooks, 12 notebooks, or 30 notebooks, we represent the number of notebooks by a variable, say n. The total cost becomes 18n. This single expression works for every possible quantity. If n becomes 15, what do you think the total is? Think for a moment. It immediately becomes 18 into 15, or 270 rupees. Algebra is powerful because one expression can represent infinitely many situations.
An algebraic expression is formed using variables, coefficients, and operations. Consider a science fair where entry tickets cost 40 rupees for students and 70 rupees for adults. If S students and A adults attend, the total collection is written as 40S plus 70A. Notice that each term represents a different quantity. The coefficient tells us the rate or value attached to the variable. Expressions like these are mathematical models. Instead of repeated calculations, we create one rule that describes the entire situation. Even though variables appear in algebra, arithmetic rules remain unchanged. Consider the expression 8x minus 5 when x equals 4. According to BODMAS, multiplication must happen first. So 8 into 4 is 32, then 32 minus 5 gives 27. Now observe another example. 6 plus 3 into the group 7 minus 2. First solve the bracket to get 5, then multiply by 3 to get 15, and finally add 6 to get 21. Letters never change operation rules. They simply stand in place of numbers. In algebra, multiplication signs are usually omitted for simplicity. Instead of writing 12 into p, mathematicians write 12p. But this notation creates a very common mistake. Suppose d equals 7. Then does 4d mean 47? Think carefully. No, it means 4 into 7, which is 28. Similarly, 2ab means 2 into a into b. Whenever numbers and variables are written together, multiplication is automatically understood. This shorthand notation makes algebra compact and efficient. Now, let us simplify expressions involving like terms. Consider a long expression like 9x plus 4y minus 3x plus 7 minus 2y plus 5x minus 1. To simplify, group like terms together. The x terms become 9x minus 3x plus 5x, which is 11x. The y terms are 4y minus 2y, which is 2y. Constant terms are 7 minus 1, which is 6. So the simplified expression becomes 11x plus 2y plus 6. Notice that only terms with identical variables can combine. Algebra follows structure very strictly. The distributive property allows us to expand expressions efficiently. Consider 5 into the group 2x minus 3y plus 4. The number outside the bracket multiplies every term inside. So 5 into 2x is 10x. 5 into negative 3y is negative 15y, and 5 into 4 is 20. The expanded expression becomes 10x minus 15y plus 20. This property is extremely useful because it converts grouped expressions into simpler linear forms that are easier to evaluate. Negative signs outside brackets require special attention. Observe this: 18a minus the group 5a minus 3b plus 7. The negative sign distributes throughout the bracket, changing every sign inside. So it becomes 18a minus 5a plus 3b minus 7. Now combine the like terms to get 13a plus 3b minus 7. One incorrect sign can completely change the final answer. In algebra, accuracy with signs is just as important as calculation itself. Algebra is extremely useful in identifying patterns. Look at the sequence: 4, 9, 14, 19, and so on. The numbers increase by 5 each time. Instead of writing the entire sequence, we can build a formula for the nth term. The pattern starts at 4 and adds 5 repeatedly. We write this as 4 plus 5 multiplied by the group n minus 1. Now, why do we use n minus 1? Because to reach the nth position, we only jump 5s after the first term, that is, n minus 1 times. If you want the third term, you only add 2 5s to the first term. Now we can find any term. For the 100th term, 4 plus 5 multiplied by the group 100 minus 1 is 499. This ability to generalize patterns is a core use of algebra. Let us examine a hidden pattern inside calendars. Suppose the top left number in a 2 by 2 calendar square is A. Then the remaining numbers automatically become A plus 1, A plus 7, and A plus 8. Now compare the diagonal sums. The first diagonal is A plus 8, which is 2A plus 8. The second diagonal is A plus 1 plus A plus 7, which is also 2A plus 8. Both diagonals simplify to the same expression. Algebra proves that this pattern works for every calendar square, not just one example.
Remember that algebraic expressions can look different while representing the same quantity. Before I go, here is a final thought. Is 3 into the group x plus 2 equal to 3x plus 2? No, the 3 must reach the 2 as well, making it 3x plus 6. Keep practicing these expansions.